Ooh.
And we're live. Hello, everyone. Hello, Federico.
Hello, JB, and hello,
How,
everybody.
how are you doing today?
Very good, very good. And you?
Yeah, good, thanks. I'm very excited to have you today
Me
to
too.
talk about particles systems. So, you'll explain in a minute what particles are about. I think this live stream is interesting to anyone who's interested in live video, interactive, complex, rich video.
Hmm.
Uh, and you also have a YouTube channel called Amazing Max Stuff. So it's
That's
all
the
about
name.
Max, but it's more specifically around live video, isn't it?
Yes, exactly. I wanted to be a general purpose Max channel in the beginning, but then I went fully into videos. And people that follow me since a while probably know that this is only about visuals and computer graphics in Max and Jitter. That's what I like the most. Hey, Kevin. Hi, Kev.
Great to have Kevin
Um,
was the one who introduced us when I was asking him if he could help with some jitter things. He said, no. Federico is the guy. So thank you,
Thank you again,
Kevin, for the
Kevin.
introduction.
Big shout
Uh,
out to you.
so yeah, that's great. Could you tell a little bit about particles? I mean, and why they are interesting for the work of live um, videos?
Yeah, the thing with particles is that you can easily achieve nice results, which is often not the case in computer graphic, especially when starting from scratch, like in an environment like in Max. So particles allow you to achieve very nice results in very few time and with not so complex algorithms. And they can there are various broad space of particle system graphics there, and you can really go from the most basic to some more advanced stuff. And yeah, in general, it's very funny because you can really experiment a lot, and it's easy to experiment.
Right, and so particle systems are like imagining a flock of birds or fishes in the sea, and like imagining their behaviors together, right? And so you have
Yeah,
attraction and
exactly.
right, right,
Yeah,
right.
yeah. There are basically two big ways how to do a particle system. You can do it in a way that the particles just interact to external forces, like for example simulating leaves in the wind. And you can have, like you were saying, like flocks of animals and in this case the particles interact with another. So this is a more complex version of a particle system, of course, because you have to take the other particles into account. But it's very, yeah. There are these two big
And
things.
isn't that too heavy on the CPU? I mean, imagining like millions of particles together, each of them has their own behavior. Isn't that too heavy on the computer
Yeah,
performances?
yeah. It used to be very heavy before GL3, before Max. I mean, talking about specifically about Max. Before they introduced the GL3 package, the only way to make particle system was either to do it on the CPU or to do it on the GPU, but was a little convoluted. And now with the GL3 package, they introduced exactly a way to create particle system completely in the GPU, which is something that was already existing in OpenGL, and they just catched up
All right,
with OpenGL. So now we can do it also in Max. So
great.
also old
So
computers now, kind of fun.
so you can have much better performance
Yeah,
and leave
yeah,
some of the
definitely. Yeah,
CPU for your audio
yeah. For
processing, I suppose.
example, yeah.
And so today you're going to present your work, and we're going to have a deep dive into your practice and the world of particles. And for those who
Nice.
want to know a bit more, also you will give a series of workshops starting on the 20th of October, and it's going to be 4 workshops in a row. Every Tuesday, starting next week. So today is kind of an overview, and thank you so much for coming. I'm going to
Thank
remove
you, GB.
myself, and hopefully your performance system with OBS will take over. All right.
Okay,
So
we
over
close that.
to you.
Cool. Thank you very much, JP, and hi everybody. I'm a bit nervous, I have to say. Although I do YouTube stuff since 5 years, I think now, but I'm always pretty. When there is a live situation, I'm always pretty excited. So forgive me if I'm a bit excited, but yeah, that's how it is. So cool. First of all, let me maybe introduce you to my website for the ones of you that don't know it. This is my website, federicofoderaro.com, and I'm showing it to you because here is where I share all my production. So if you go into Amazing Mac Stuff into video tutorials, you can find all my videos that I made in those years, and they are organized with tags. So if you go into, for example, particles, here, you can see that there are almost 20 videos. And these are all my tutorials about particles. You click on it, you go on YouTube. As you know, actually you go first to my Patreon, and then you can watch the video which is hosted on YouTube. So, but if you didn't know about my website and the tag system, that's how it works. And then, for example, if you go into patches, you can see all my patches, which some have some also YouTube videos, so you can check how the patch looks like on YouTube. And some of them are also for free to download. All my video tutorials are for free to watch, of course. So yeah, that's basically a good resource when you want to learn about visuals in Max, modestly speaking. So cool. I did prepare a little patch for today. As let me actually do one thing. Let me put this on my other screen. Thank you, Bresciani. Sorry, I don't remember your first name, but thank you very much. I did prepare a little patch for today, but I think I'm not going to use it because it's actually not working completely. So instead, let's actually talk a bit about particle system like JP introduced. So let's start with a very simple particle system. So let me save this patch, and let's call it particles stream. Okay, so let's do some maxing, some patching. So as you know, to do any kind of computer graphics in Max, you need a JIT world object. Call it stream. Now this is the name of the context, and then let's give it like a full-scale anti-aliasing attribute, and let's give it the erase color attribute to erase the color of the background. And okay, I don't want this to be too much similar to my tutorials. So if you got questions, please stop me. So this will make it a bit more entertaining than a basic tutorial, basically. Okay. So what I like to give always to the world is a floating attribute, which will make the window stay on top of the patch. And maybe let's start with some window dimension. Whoa, this is very big window by mistake. 2400 pixels. Nope. Okay, cool. So the thing is, we can create a particle system, as I was saying before, in two ways. One way is to create it on the CPU, which is the easiest way, and the other way is to take advantage of the GL3 particle system technique. So we are going to first create a little particle system simply using like the CPU. So we're going to do it using JIT-gen. Whoops. There will be a lot of mistyping in this session. Thank you, Blippenspiel. Thank you, man, for recognizing me. So, so yeah, exactly. We create a little JIT matrix here with 3 planes, from 30 to 100 cells. Now, if you know a bit how Jitter works, I see we have a question from Linkcell. The topic is going to be about particle system. Yeah, so the topic of the workshops with Music Hack Space is going to be about particle system, especially how to create them using the GL3 package. And yeah, this is going to be the topic. So yeah, we basically have a JIT-gen and a GGL mesh. So the GGL mesh takes the name of the JIT world as a context, because it needs to render to that context. And then we usually, when we work with particles, we give it the draw mode points. So this means that the vertices are going to be represented as points. So if we do this, if we activate the JIT world with a toggle, nothing is going to appear because these points are all at the point 0, 0, 0, and they're actually pretty small. So let's make them bigger. And of course, I need also to bank this matrix. Cool. So now you can see there is a little point here in the center of the window. I'm banging the matrix here with the bang that comes out from JIT world. So this JIT world will put out a bang at every frame. So you can see that at every frame is sending out a bang. And by default, we got 60 frames per second. So if we create a JIT FPS GUI object, we can see that it's giving us 60 frames per second. So our frame rate at the moment is consistent into 60 frames per second. Great. Then, for example, let's go inside JIT-gen and let's create a SNorm object. Now, JIT-gen is this environment inside Max which allow us to create our own matrix operators, basically. And there's a lot of nice built-in features. So one of the objects which are very useful, for example, is the signed normalized coordinates. And this object gives us normal coordinates for every cell in this matrix that comes inside, but they are signed between -1 and 1. Normalized because they go between -1, between 0 and 1, but signed, so they go actually between -1, then they go all the way to 0, and then from 0 all the way to 1 again. For every axis of our matrix. Now, our matrix being a one-dimensional matrix has only got one axis, so we need to, this is why it's representing the vertices like this, because it's going between -1 and 1 for the x and -1 and 1 for the y. If we do something like this, create a vector tree, and connect this only to the x position, we can see that the vertices are all on an horizontal line because the x-axis is set to 0 and the x-coordinate of this vector is set to 0 as, sorry, the z-coordinate is set to 0 as well. So only the x-coordinates get modified. Yeah, sure, this will be online on Music Hack Space YouTube channel. Sure, JD can confirm that. So let's give it actually a color to these particles. Let's make them white, so we have a bigger contrast with the background. And for example, if we change one of those numbers, for example 0.5, we can see that the particles are now all at the 0.5 position with the y. I'm already calling them particles. Actually, they're just points. So vertices represented as points. We could also represent those vertices in a different way. We could represent them like as lines, as line strip, triangles, and whatever. But we decide to represent them as points because particles are usually represented as points. But this doesn't mean that this will be always the case. Cool. Now let's go into the the actual source of the particle system on the CPU. Oh, to change the color of the background, it's really easy. It's done with erase color. So we could actually also create a swatch object. This guy, it's called swatch. It's just a color selector from a palette of colors. And we can say then prepend erase color, which will prepend the word erase color to this thing. Then we connect it to the JIT world, and we can change the color of the background. So that's very nice. We can make more interesting backgrounds in different ways, but to have a basic color thing, this is the easiest way to do that. It looks pretty nice. Yeah, triangles didn't show up because the particles, the vertices are all aligned in one strip, which doesn't really go well for looking like triangles. They just disappear basically because they are not aligned in a way to be represented as triangles. This is not so straightforward. You cannot just say triangles, then little triangles appear. The vertices must be ordered in a certain way. Thank you, my friend. That's really nice. I am really flattered. So, as a general similar functions, the general experience is not similar at all. Yeah, it's basically like the gen object works on single samples, and the JIT gen works on matrices, but working on single cells. Working on single cells one at a time. So it's basically the same, but one works on samples, the other works on cells of a matrix. But I think they share a lot of the operators. I never used. I mean, I think I never used gen for the MSP, but it should be pretty similar. Yeah. Also in how it was thought. Cool, so I was saying, let's get to the juice of this thing. So what we will do is to first create a JIT matrix 3 float 32 100, which we will put on top of here. Yeah, it's not really necessary at the moment. So let's give actually a name to this matrix, and let's call it position. Now, what is the thing? If we have two matrices that have the same name, whatever comes up in the first matrix, so for example, let's fill this with a JIT noise. Whatever comes up in a matrix that has a name will show up in the matrices that have the same name. So this matrix here has exactly the same content as this matrix here. So that's because they have the same name, so they access the same place in memory. So this could be pretty useful for a lot of things. And in this case, will be useful for our particle system. Now, I see a question: how does SNORM know which input to process? It doesn't work on inputs. It works on how many axes this matrix has. So if this was a 2D matrix, let's make it very clear. If this was a 2D matrix, and we will do something like this, switch X and switch Y, now we will have, on the X-axis, we will have the X coordinates. As you can see here, they are represented by the color red. Let's put the green to 0. Okay, so if we represent the matrix as colors, you can see that basically this goes between -1, rise to 0, and then it goes to 1 on the right. Now the Y will do the same, but on the Y axis. So we go -1, and then a rise to 0 in the center, and then it goes to 1 on the bottom. So it doesn't work on inputs, it just works on axis, because if we just have one axis, then the Y, it's just the same as the X. It's actually empty, it just takes the same value as the X, because we just have one single dimensional matrix. So it works with dimensions of the matrix. In this case, it's one-dimensional. In this case, it's two-dimensional. In this case, it's three-dimensional, four-dimensional, whatever. It doesn't matter which number I write inside. It's just about how many dimensions I actually assign to this matrix. So these are all dimensions. Above 3 dimensions, our human brain cannot visualize it graphically, because we live in a 3-dimensional world, at least on a physical level, and so we cannot visualize our matrix with 6 dimensions or 7 dimensions looks like, but you can feel as many dimensions as you want inside a matrix. And every dimension will have the number of cells which you write in these numbers here. I got a couple of tutorials about matrices. Let me fetch them for you. So if you go here and if you go into beginners and you don't feel ashamed because of that, you can see that there is a tutorial, Prelude 01 JIT matrix. Then there is, let's start with Jitter. What is a Jitter matrix? This is and then the subsequent one, create images with JIT matrix. I think these 3 tutorials are pretty good to understand what actually a matrix is. Okay, cool. Okay, now let's go back in our particles world. We were shortly landed in the color world, but this is not what we want to do today. We want to go into the vertices world. So we're not going to interpret those numbers as colors, as value for a color. We're going to interpret them as values for some position in a 3-dimensional space, which is where our particles will be. So I was saying, since these 2 matrices have the same name, whatever happens in the first matrix will happen also in the last, and vice versa. So if this matrix gets modified, this matrix here will be modified as well. So let's actually not connect the epsilon exactly. So what happens if we do something like that? Instead of saying as norm, we use actually the input one as our input. Let's actually connect the x and y. So as our container for the values of the vertices. Now, of course, this is empty because, of course, we can fill it actually with a JIT noise, but by default, this was actually an empty matrix. So if we just create a matrix, it's going to be an empty matrix, which means all the numbers inside this matrix are going to be 0. We can actually check that using a cell block. And then we can give it plane -1, which will show us all the plane of the cell box. And then we can actually make the columns a bit wider. We can see actually all the 3 numbers. We can see that all those values of this matrix are actually 0. Okay, so it's an empty matrix. So let's initialize this. Instead of having just an empty matrix, let's initialize this with the signal normalized coordinates that we had before. So let's go here. And let's create, as we did before, let's create a nest norm. And then let's switch the x component. And let's connect it as the first component of a vector 3. This I call vector 3 because it's a vector with 3 components, and we are just going to fill the x. So we are where we were before. We just got all the vertices that goes on the x-axis between -1 and 1. And we can also see that on the cell block, which will show us that actually the numbers go between -1 on the left, so on the first cell. This is the first cell, this is the second cell, third cell, and so on. We have 100 of those cells. So it goes between -1 and actually 1 on the right. Okay. Cool. So now we are using those values that are inside this matrix as our input for the JIT gen. Okay. So what happens if we sum to the y-axis a small quantity at every frame? So you can see that the particles or the vertices, the dots, start to rise until they will just go away from the window. The bigger we make this number, the faster they are going to raise up. And as you can see, the numbers in this matrix are getting bigger and bigger as well. Now, why is that? That's because the values that are inside this matrix get banged at every frame from the JIT world through this cable. Let's make it red. And so this is banged at every frame. At every frame, the values inside this matrix go inside the JIT gen. The y value gets added to this little quantity, and those values go inside this matrix at the bottom of the chain. But then on the next frame, the values inside this matrix have been updated to the modified values that were inside this matrix here, because they access the same place in the memory. So that's why the number keeps growing. It's like if you stored the values from the previous frame, and then you access them again on the next frame. That's how you basically pass values in Jitter between one frame and the other. So instead of starting from scratch every time, it will start with the values that it had on the previous frame. If we detach this matrix here, you can see that nothing happens, because what is the thing? The values come inside. They get summed to the small quantity, which we can also make it a bit bigger so we can actually see it on the cell block. Exactly, but then on the next frame, they start again from scratch with the initial values of this matrix, which was the signed coordinates on the x-axis. Okay, while if we connect this matrix, we achieve this kind of for loop. No, it's not really a for loop, it's like just a loop. And yeah, we can actually have a state stored in memory. That's how we store the state of this particle system at every frame. Okay, questions about this? Because this is actually the core of the thing. So once this is clear, the rest is going to be just like a breeze. So, cool. Seems that there are no questions. Amazing. So we can actually go on. As you can see, the particles will disappear on top of the screen once they go too far up. And in order to avoid that, we can actually just wrap them between -1 and 1. So now whatever axis they are, so all the three axes, x, y, and z, are wrapped between -1 and 1. So this means that when the particles go above 1, they will come back up. They will come back at -1 on the y, and the same thing they will do on the x and on the z. So this is a way to kind of keep them inside. Nice, thank you. So this will be a way to keep them inside some sort of virtual cube. Let's actually add a little camera to our patch, so we can actually move around in the world. So we will do that using a jit anim dry. We give it UI listen, and we give it a speed which is quite fast, like 20. Now we create a GGL camera that goes to stream, that looks at 000, which is the center. Then we lock the look, and then we do something like tripod 1, which makes the camera not tilt, so the camera will like be on a tripod. So then now we can move using the WASD keys in our patch, which is pretty cool. And in order to reset the original view, we go with anim reset. Zack, zack, zack. Cool. Anim reset must be connected both to the anim drive and to the camera. Okay, great. Let's, for example, try to attach a jit noise to the initial matrix. Let's delete this jit gen. So, of course, the jit noise just goes between 0 and 1. That's why the particles are all on this left, on the right top side of the screen. Wrap equivalent to modulo? No, it's not equivalent to modulo, because modulo only takes one number as an argument, which means it will just return between 0 and 1. So it always goes back to 0. Okay? So let's show this here. If we go with modulo 1, and we go between 0 and 1, then we'll go back to 0. But it doesn't go to -1. It doesn't have a range, because it just does the modulo of one single number. It doesn't do a range. While if we do wrap, then we can actually choose our range. So wrap is just an evolution of the modulo, basically. So yeah, they're quite related, but not exactly the same. Okay. So yeah, since the noise only goes between 0 and 1, we can actually use the jit.map object and remap this range. So map 0, 1 between -1 and 1. So we basically remake the values of this noise between -1 and 1. So now our particles are a bit more around in the space. And we can actually start to use also the z-axis. So let's switch the zeta here as well from our input. Let's connect it to the z-axis. And let's build this again. Cool. So now we have three-dimensional particles. And see our particles raising up and disappearing here. We can do something pretty nice. We can have our second output, and simply we can simply wrap their position and assign their position to their color. So for example, we can scale -1, 1 to 0, 1, so get the y-axis, and use it as a mixed value. So this will be our mixed value between two colors, for example. Let's say, for example, red. This is going to be red because we are only 3 planes. So if we got only 3 planes, these are going to be interpreted as red, green, and blue. If we had 4 planes, we would have the alpha at the end. But we only got 3, which is okay. It's going to be like red, green, and blue. And then let's have like a green color for the... Is this how you make green? I'm actually not sure anymore. Okay, when the value is 0, they will be red. When the value is 1, they will be green. So if we connect the second input to the color array input, cool. We can see that the particles start red when they are at 0, and then they will actually go up until they become green. That's pretty nice. It's a little trick. So we can use basically the state of the particles to change the color of the particles, for example. One thing I don't like is that when they start up, they are actually still green, which is not something I like. So we can actually say that's happening because maybe let's try this. No. Okay, then let's say, let's scale -0.9. No, let's scale -1.1. No, of course. 0 to 1, so red. Oh, okay. It's above me at the moment why they start green. If somebody has a solution to this little bug, please let me know, guys. Anyway, it's not such a big deal. We could also make them disappear. Could also make them disappear. But cyan, green, and blue. Okay. Yeah, we could do them also. Cyan. We could do all the colors we want. And I have created the yeah, sure. Actually, for green, it's just like that. God. Okay. Yeah. Sorry. Thank you, Dublarty. Yeah, I was completely fried up on this thing. Okay, amazing. So this is actually green. Before it was cyan, as Dublarty said. Cool. Let's now introduce some more interesting behavior. So, for example, we could actually use this instead of just animating dots. We could use this to animate like images or videos even. Okay, so in order to do that, we have to use a GGL multiple. And this is going to be a little trip now that we do into the GGL multiple realm. So the GGL multiple takes a couple of arguments. One is the context where it draws. The second is how many parameters it's going to change for its target object. If you're not familiar with GGL multiple, what it does is it takes a target object and it replicates according to an input matrix. So for every cell of the input matrix, it creates a copy of this object, of this 3D object. So then it takes the argument GL params. So let's say position, scale, and rotation. It's called rotate x, y, and z. Cool. And great, let's create a target. So let's create a GGL grid shape that draws to stream as well. Shape plane. Going to have, I would like to have like leaves, like autumn leaves. Since we are in autumn, I would like to have autumn leaves going up in the sky, so from the ground to the sky. So we will do something like that. Let's give it automatic 0. Let's give it a color of 1, of white. And this will be our target, so we just need to connect it to the GGL multiple. And now I just duplicated this JIT because I want to keep this JIT down on the side, and I want to create a new one and work on this one. So we need to give it another output for the scale of this object. Thank you, JB. Now we're actually only just scratching the surface, really. This is actually just scratching the surface, as people that know my tutorial know. So let's give it, for example, a scale value of 0.1. And let's make it 0.2. Will be a bit bigger. So let's connect this to the scale input. Okay, exactly. So now we have a bunch of quads just floating up. Let's actually disable the GGL mesh. So I will give it enable 0 so we don't see the dots anymore. Good. We just have a bunch of grid shapes. Now, let me get an image of a leaf. So I will just go on internet, look for leaf autumn. I will probably get a copyrighted image, which is okay. I will just save it on my desktop. So I found this image. Okay, so this is the leaf we are going to use. So let's give it a human name, and let's call it leaf JPG. And let's load it inside the texture. So let's create a GGL texture here, which goes to stream, and that's everything we care about. Actually needs a name. Let's call it leaf texture, leaf text. And let's read this leaf inside this texture. So let's say read and let's say leaf.jpg, since they are both on desktop, we should find actually this image. I think it now contains this image, this texture. You can actually check this out using a jit.pix window. And cool. So it reads this image. Oh, this can actually be linked. So yeah, we have to check this out. Cool. So now this contains this texture. We can actually assign this texture like this to this object, texture leaf text. Cool. Now we got a bunch of leaves. We got a bunch of leaves just going up. What is not really nice is the fact that they are still, they don't look like leaves. They look like a bunch of images of a leaf. So let's actually enable the blend, the transparency for these quads, and make them transparent when the background is white. So in order to do that, we go here on this object, and we enable the blend enable 1. We then disable the depth enable 0. Maybe we don't need to disable the depth. Let's leave it to 1, which is the default for the moment. Blend enable will enable by default. The blend will be alpha blend. This is what we got by default. So we will make it in a way that when the color is white, those the objects are going to be completely transparent. So in order to do this, we can actually do this on a texture level. So we see another way to use the gen language. We are going to use the gen language using jit.pix. So jit.pix is like the same as jit.gen, but it works on this GPU instead of the CPU. Hello, Dean. And it works only with textures. So it works with matrices as well, but it's going to interpret them as texture, which means it only works with 4 planes. It assumes everything that comes inside to have 4 planes, because textures always have 4 planes. So what we're gonna do is to switch the red, the green. That's probably a better way to do that, but we're just going to do that. Actually, you can do this all with an expression. So we also take a look at how expressions work inside JitGen. So an expression is like our little line of a little function that we can write inside the gen. So instead of writing multiple objects, we can all do the same. We can have the same result just by writing the stuff inside an expression. So we can say input1.r plus input1.green plus input1.b, so the 3 channels. So if we sum them together and then divide the result by 3, if we have a white color, we will have the value 1. So let's say if this is greater than 0.9, it will give us a 1. And if this is not the case, it will give us a 0. So what we can do then, let's try, for example, just to output this. So let's bang this, and exactly. So this is what we have as a result. Now we actually want to get the opposite of that. So let's just say if this is smaller than 0.95, for example, and we get the opposite. And then we want to multiply that by our texture. We will have only the leaf and a black background. So now let's actually don't give a name to this texture. Let's actually give a name to another texture that we attach here at the end. So exactly. So now basically we got rid of the background of these images. Now, as you can see, if you keep the depth enabled, we will have some artifacts, which means the image is going to look glitchy because some images are before some other ones. which will make the effect look bad. So we actually just need to disable the depth. Good. And now it's going to look a bit better. It's also still going to look glitchy. In order to have it perfect, we will have to reorder those images according to their zeta value, so where they are in the space in the z. But this goes above the scope of this streaming session, so we're not going to do this now. Let's actually put a nice load bang here. So when we open the patch, we get the leaves. Cool. And nice. So now let's give to these leaves a different scale. So we want them to be some bigger, some smaller, and so on. So we're going to do this using a jit noise with only one plane, because we're going to use only one single number for every cell. Okay, for 32 and 100 cells, because we want to have as many cells as leaves. So let's bang this. Good. So now we got the second input contains the values from this noise. Let's anyway switch the x, because anyway this is going to be a 3-plane matrix when it comes inside, because it's going to be adapted to the plane amount of the matrix that comes in the left. So it's always going to be 3 planes. So we actually just want to switch one single plane. Now we can actually multiply this, for example, by 0.2 and assign this as the scale value. Cool. So now some leaves are going to be extremely small, some are going to be extremely big. So let's actually reduce a bit this effect by adding an offset, multiplying this by something really smaller. So exactly, so there is not going to be such a big difference between the smallest and the biggest. You can also make it a bit more subtle by giving it only just 0.3. That's maybe too few. 0.5, exactly. So now the smallest one is going to be when the noise has a value of 0. So it's going to just have a size of 0.1, and the biggest one is going to have a size of 1.05. when the value of the noise is going to be 1. Okay, and in between we get all the stuff in between. Okay, are there some questions about the things that we did? Did everybody already escaped after they saw the autumn leaves? They thought this looked like my grandmother style. I hope not. I hope somebody's still there. Anyway, we can change the size of these fellas with the noise. Okay, cool. Let's also have like another blend type, like add, which then looks a bit strange. Color blend doesn't really work. Alpha blend is actually the best we got for the job. Good. Thank you, guys. Thank you for tuning up. Great. Okay, now let's actually rotate those leaves, because at the moment we scale them. We now want to rotate them. So let's actually use the output 2 as the scale. We're not using the color for the moment. So let's actually use the output 2 as the scale. So let's connect these here. And then let's create an output 3, which we will use for the rotation. So thank you, EBB 30K. Okay. So let's make them rotate. So how do we do that? We can, for example, still use the scale of the, this was actually scale -1, 1. Why was this 0 to 1? It's wrong. In any case, -1 to 1, we scale to 0 to 1, and then let's apply this to rotation. So let's multiply this value by 360. So they will make a full rotation from the bottom to the top. And let's apply this since we are using the rotate x, y, zeta, let's apply this to the zeta rotation. So they will actually rotate on the axis, and they will look like leaves rotating on the z-axis. Exactly. That's how it looks like at the moment. But they're all rotating at the same time, in the same way. So let's actually improve that, and let's create another plane for the noise. Let's create 3 planes. So in case we need them, we got a couple 2 random values more. So let's go inside here. Instead of switching the x, let's switch the y, so we get completely different values. And cool, we can actually multiply these, or simply add these to the noise value. So we then, hopefully, we will have a completely different rotation for the leaves. Exactly. So as you can see, they all start rotating at a different point. Maybe it will be more interesting if we if they actually rotate at a different speed. So in order to do that, maybe we just need to, no, that's the same. So in order to make them rotate at different speed, we just need to modify the scale. So let's try actually like this and multiply this by 4 or something. Not sure this is actually going to work. Yeah. Okay, exactly. So now some are rotating faster, some are rotating slower. Let's actually make it by 2. And then let's add the offset so we don't have leaves that are completely stuck. So let's add like 0.5 as an offset. Okay, great. So some are rotating faster, some are rotating slower. So let's see if you change alpha of erase color with this. No, this just worked in GL2. And I'm actually on GL3. I didn't mention this in the beginning. Sorry about that. But I'm actually on GL3. So the smear thing will not work. To make the smear thing, we can do it still, but we need to do it in a different way. If we have some time, we can do that. Anyway, exactly. Thank you, JB. Okay, so now they are rotating on the z-axis. Let's maybe try to make them rotate on the x-axis as well. And of course, we need to multiply as well by 360. So let's actually connect this to the 360. Exactly. Yeah, it doesn't look super realistic, of course. We could actually switch the. We could actually have another thing, switch the z of the noise, that component, and then apply these as the x rotation. So we got 2 different speed of rotations for the x-axis and the z-axis. Okay, yeah. Let's actually make it a bit more natural. So let's make them go from top to bottom. To do that, we just reverse the sign here, which means, oh, why have they not reversed? Should actually go the other way around. Have I missed something? Yeah, of course, because we are actually still using the position that comes from the other JIT gen. So I made a bit of confusion here with these 2 JIT gens. Let me actually remove this position matrix from here. Let me actually remove this JIT gen completely. And we are going to attach this JIT position after the position output here. Cool. We now go from top to bottom. Maybe we want to have more leaves. In order to have more leaves, we just need to change the dimensions of this matrix. And don't worry, this is not going to be super heavy on the CPU, because since GL3, the GGL multiple works using something called instancing, which will recreate the shapes directly inside the GPU without sending at every frame. No, we'll just send the whole instruction to the GPU once per frame, basically. So it doesn't seem they got be more. Yeah, actually they did. Okay, so we need also 300 noises. Okay, now we have 300. Let's get like 1000 of these. Let's actually make this dynamic. So let's create a dimension thing, which will then can apply to all the matrices involved here. Let's get let's get like 1000, right? And then we need to bang this. Does it look like 1000? Because we need to change the dimensions also of that matrix. That's why it was not changing. Sorry about that. So we actually need to bang these. All right. So that's how 1000 leaves look like. A bit too much. Let's go back to 300. And let's actually attach a bang after we do this. So after we do this, we bang these matrices and they go, and they actually output the matrix. So this is important for this initial matrix here. And cool. So we got a bunch of leaves. We can make these a bit more nice, for example, by making them completely disappear when they arrive at the bottom. So in order to do that, and then I think this is the last thing we do, then we step into the Q&A session, if this is okay with JB. So let's do this first.
Absolutely. Absolutely.
Okay, thank you. So let's first do this thing. So basically, instead of using the red and green thing, let's create another output, make output 4. And so we scale -1, 1 to 0, 1. Okay. Okay, let's just use this as the alpha value of a color. So let's just go like this, jit.pix 4, now 1, jump 4. So this means that it's just jit.pix. It's going to fill a matrix with 4 planes using a single plane of the input matrix. Well, actually, we should do something like that to be extremely precise. So to be explicit, we basically unpack one of these 3 planes from the input matrix, because this is a 3 planes matrix. We take one of those planes, we attach it at the JIT unpack. So we unpacked one of the planes, we put it in a jit.pix, so now we have 4 planes that have the same values instead of 3. So why is it important to have 4 planes? Because we need the 4th plane, which is the alpha. So then let's create a 4th parameter here for the GGL multiple, which is the color. As you can see, they became black because by default the value is 0. And okay, everybody's gone. Can you imagine cleaning all those things? Not my job, guys. So, yeah. So why is this not doing what I want? Let's check. What do we get? This doesn't look right. This doesn't look right. So let's connect it here. Okay, this looks right. This looks right as well. Okay, then there is something wrong with my understanding of the jit.pix. I thought it was like this. Probably not. Probably not. So let's actually do it in a very kind of dumb way. So we just fill the same matrix with the same plane. Cool. So now we got the leaves that go from full colored to being completely transparent and disappearing. We can actually decide better the range for these. So when they start actually to disappear, we can decide this better. For example, with a smooth step. So we can say below the value 0.5 is going to be 0, and then between 0.5 and 1 is going to give us a smooth transition, but the other way around. So we just reverse it. No, actually, this was correct. So between, sorry, let me 1 second reason about that. But when this is -1, they're going to be 0. Exactly, so 0, 1. So smooth step 0.51. If we go 0, 1, it's the same. So we actually have to say 0.2 exactly. So we get a better control of when they actually start to disappear. So if we go 0 to 1, it's basically going to be the same. It's just doing a little curve. And if we say 0.5, they start to disappear when they actually arrive at half of the way. Then they will start to disappear in a curve. Can even make them become smaller. We can make them become smaller like this. We can simply multiply the scale by the value that we get from here, so they become smaller. We can actually use the same smooth step thing, exactly. Or we can also create another smooth step thing. Oops. And say, for example, they just become smaller when they are between almost the end and the end. Exactly. So now they become smaller when they arrive here at the end. Something like that. Can make these a bit bigger. Oh, it can actually, it's also cool without this, is a bit more dreamy. Yeah, you can choose that. It's a matter of taste at this point. But you have the elements to get this to work. Okay, cool. I think maybe we stop here. What do you think, JB?
It's up to you. If you have more materials that you want to go through, I can
mean, I
watch
could
you.
go on forever.
Yeah,
I could go on forever, but
well, maybe we can leave some for the workshop. So
yeah,
we have
exactly.
a great workshop coming up soon, next week. And maybe, I mean, a question for me, and then
Yeah.
we can take more questions from the streams on Facebook and YouTube. What else people will learn from the workshop?
Okay. So basically, as I thought it's going to be very centered around how to create the particle system using the GL3 system. So if we take a look, for example, at the package manager, let me check if I got it. No. So we go into GL3, launch. Let me actually stop the patch. So for example, billboard particles. All right. So it's a pretty nice patch. So we're going to see how to create the particles using the system using in this example patch from Cycling74, which is basically to use this object called GGLTF, which allows you to create mostly particle system. It cannot be used for much else, I think, using shaders. So basically, we are going to understand how we can write this kind of stuff, how this actually works. We are going to go through the examples, see how the example themselves work, and then we're going to create examples of patches of our own. So this is going to be really about this. It's going to be about shaders. So we're going to start from scratch with shaders. We don't need to have any shaders knowledge. We are going to, do this kind of stuff, which allows them to have like, oh, this is interesting. It's doing some kind of glitch. So this allows us to have like 20 million particles. I made like a patch with 20 million particles, allows us to have better effects for the particles. If you take a look at I made like a patch here, just to show you quickly. This one I'm pretty proud about. This is done completely using the GL3 system. If it loads. Should load, because I'm actually connected to the Edward match. Okay. So like these kind of things are really funny, and these kind of effects are very difficult to achieve without using the GL3 package, and actually some are really impossible to achieve because of how you combine the elements and how many elements you have. Like this is, I don't know, like 1,000 cubes or more than 1,000 cubes, and they explode and they become smaller, they change color, they glow, which is also pretty nice thing. And this is all very difficult to achieve without the GL3 package, if not impossible. So we will learn this kind of stuff, basically.
Amazing. So pretty much everybody who has some experience with Gen and discovers GL3 would be able to get by the end of the 4 sessions to build a video like the one you just showed.
Yes, definitely.
The marching cubes. That's great. Oh, that's fantastic.
Marching cubes, yeah, not really this algorithm, but it's not really marching cubes algorithm, but yeah, it's cubes and they are marching around.
Right. So we have a couple of questions. Chris Speed Visuals is asking.
Hey, Chris.
A question here.
Thank you. I just want to use a way to optimize video playback using the GPU in Jitter. The opcode is a bit tricky to set up on Windows. Yeah, it's a bit tricky, but it's actually still the best option. So basically, in order to play a video the best way possible, you do this thing with the app codec, which you can do on some Adobe encoder program. There are some iMarco. There are some drivers for the Adobe encoder thing, and then you can get a video as an app file encoded. Then you go into the JIT movie. You say output texture, and then you give it automatic 1. You give it the draw to context, which in this case is stream. Then, for example, we can load a video like the chickens one, for example, which is full HD. And then this is going to be pretty fast. It's already pretty fast by default, even without the app codec. You can play, I can play, with my computer, I can play a bunch of those, I suppose. And the computer is still going to be at 60 frames per second. Yeah. So already output texture is a very good way to play videos at a good frame rate. So if you want even best result, then you do this thing with the app. I know it's tricky. I also bang my head around it quite a while, but it's feasible. And if you really need to play, like, I don't know, 8 full HD videos or 2 4K videos, then that's the way to go. Yeah. So now
we have another question from Linkcell.
So Linkcell, can I have one for running camera? Which video I should watch? Yeah, this is something that I always do in my videos. So if you look at a couple of my videos, this will come up. Anyway, this video that we just streamed is going to be online, so you can rewatch it at this part. And anyway, so the look at thing is to look in the place that you want. For example, I want to look in the center. I give it the coordinates of the center. If I want to look on the right, I give them coordinates to look like in the right. Sorry, let me just disable this video plane. Okay. The look at is basically where the camera should look. So if you go on the attribute here, and we say, okay, look on the right, look on the left, or look in the center. Then
so
look. Yeah.
So if you wanted to connect like a joystick or even the arrows of the computer, you could do that and navigate directly into your space.
Yeah, definitely. So for the moment, for example, now I'm using WASD keys on my computer. This is set inside the animate drive object. If you double click, it gives you this. You can say with which keys are used to move. But you can, of course, also hook up a joystick or a joypad, and you can do it. I don't remember if you can do it with animate drive, but you can definitely attach the joypad to the animate drive and then get it to work in the same way. It's definitely feasible. It's not complicated. And yeah, the lock look is just to lock the look at this point, and the tripod is to not make the camera tilt. And the UI listen here means that the object works with the WASD keys, otherwise it will not do that, and the speed is just how fast this moves. So I hope this is clear enough, but it's really not difficult.
Well, this is great. We have another question from Andre.
Mm-hmm. Thank you, Andre. Okay. Basically, there is a manual for these objects. If you go into the help reference, so the help of Max reference, then you go here and you look for Gen. Then you go into documentation. There is Gen overview. So this will tell you what these operators do. So for example, if I look for Switz, okay. The Switz operator applies a Switzel operation to vectors. Yeah, of course, if you don't know what a Switzel operation is, it will be a bit tricky. In GLSL and similar series language, vector components can be accessed by indexing the vector with named planes. Exactly. So basically what this means is like you have a vector with 3 components, for example, and the Switz is just like sucking out one of the components from this vector. Okay, so that's everything it does. You can switch also multiple components like red, blue, and then again blue and green, and this will give you return a vector that contains those components from this other vector. And if you give it just only one component, it will return you a scalar, so a non-vector value. And if you give it more components, it will return you a vector. So in this case, for example, a vector with 4 components. Anyway, this is the place to go. Gen inside the Max help. So in general, when you're looking for resources, that's the place to be. And if I may say so, I made a series of tutorials about all the Gen objects. I think I covered mostly all of them at this point, which start here. So Jitter's Gen from 0 to hero, all the objects. It's
Amazing.
really quite didascalic. So you can check basically all the objects that you have in Gen, or mostly the most used ones. I think I covered them all, but if I didn't, please let me know, so I will make some more videos. And yeah, hope it's probably, I hope it's clear enough. It's always, can always be some more questions, but there's definitely a place to look at.
I have another question. I noticed that you are on Windows, and in your
Yes.
experience, is there a preferable platform for high performance video between Mac and Windows, even Linux?
Yeah. Yeah, Mac sadly doesn't run on Linux, so this already kind of cuts it out from the equation. Although there is a way to make it run, but it's a bit hacky. Then Mac, I used to work on a Mac, but then at a certain point, the cost performance that I could get out of a new Mac will then be so great as what I could get with a Windows computer, because they're immensely cheaper. So at a certain point, it's just a matter of what you get for what you spend. So with a reasonable amount of money and a Windows, you can really get a great machine. Of course, you have to deal with Windows nuances. So all the driver stuff, Windows problems, stuff that suddenly doesn't work anymore, which doesn't happen so much with Apple. So I totally like so much the Apple operative system, but sadly I could not get the same amount of, for example, the same graphic card, the same processor, the same amount of RAM with a Mac. Like this Mac, if this computer was a Mac, would have cost me, I don't know, 4 times the same.
Oh, that's
So
incredible.
yeah, that's basically the main reason. I didn't find major problems working with Windows. I have to say, I actually like the experience. I will not go back to Mac anytime soon. For a working computer, maybe I will get an iPad or something just to watch YouTube videos. But yeah, you get the idea.
Okay, well, maybe we can both come back and conclude today. So, well, thank you very much. It was amazing
very
to
much.
see
Thank
you
you.
present amazing Max stuff. It's as
Thank you
amazing
very
as it
much.
says on the tin. No, I'm really glad that you have this workshop, and then we can continue to organize and curate more if you'd like to in the future, and if the people want to see you back, it'd be really great. So we have your YouTube channel, Amazing Mac Stuff, your website, federicofoderaro.com, with all the tutorials. Pretty much all Gen objects are covered there. If there's one
And a
missing,
lot more.
you know who to ask. So that's great. To conclude, our next live stream is going to be with Andrew Osler, and we're going to go in a different direction. Andrew Osler is the founder of Expert Sleepers, that some of you may have heard of if you're into modular synthesizers. And Max is a go-to software to actually communicate with Expert Sleepers products. Very excited to announce that in the coming week. And well, thank you everyone for watching and joining.
Thank you.
This
Thank
live
you very
stream.
much, everybody. Thank you for watching, really.
And Federico, I'll see you very soon.
Thank you, JB. Thank you for having me. It was really a pleasure.
All right. Bye-bye.
Ciao, everybody.